Recall that until now we have looked at the Lebesgue integration formula for simple measurable functions and unsigned measurable functions. So in this lecture we will look at the Lebesgue integration formula for complex measurable functions. So let's give the definition for absolutely integrable complex measurable functions. Absolutely integrable complex measurable functions. So let x b mu be a measure space, and let f, which is a map from x to the complex numbers, be a measurable function. Recall that this means that f pulls back Borel sets to measurable sets. So this means that f inverse u belongs to this sigma algebra B for any Borel subset u of C. So the Borel subsets are elements of the Borel sigma algebra generated by the open subsets of C. So we call a complex function measurable if this condition is satisfied. And so for a complex measurable function f, we say that f is absolutely integrable if the integral over x of the modulus of f d mu, this is finite. So this is a complex number, and we say that when it is a finite complex number, this is f is called absolutely integrable. And so we can define the space L1 of x mu. This is the collection as the collection of all absolutely integrable functions. Absolutely integrable functions on x. So notice that here L1 x mu has information both about the measure mu as well as the sigma algebra B. So we don't usually write L1 x b mu. We suppress the notation somewhat and just write L1 x comma mu, and even sometimes also denoted by simply L1 of x. So when the measure is clear, we don't have to repeat the notation for mu always, and we simply write L1 of x. Now the quantity for an absolutely integrable function, so if f is in L1 x mu, we write the L1 norm of f as this finite quantity of the integral of mod f d mu. Further, we can make the following definitions, that if f is real valued and f belongs to L1 x mu, then we define the Lebesgue integral of f as integral of f d mu. So notice that we only worked with mod f, which was an unsigned measurable function, but here we have replaced it with f. So f is real valued, but we can break it up into its positive and negative parts, and then we are back to the unsigned case again. So we can write it as f plus d mu minus f minus d mu. So where f plus is the maximum of f and 0 and f minus is the maximum of minus f and 0. So these are the positive and negative parts of the real valued function f, and we define the real Lebesgue integral for this real valued function as the difference of these two unsigned these two integrals for the unsigned measurable functions f plus and f minus. Similarly, if f is complex valued and f is in L1x mu, then we define the complex Lebesgue integral of f as this is the integral of f d mu, and it's now we can break it up into its real and imaginary parts, which are both real valued, and so we have already defined what is a real valued what is the integral for a real valued function. So now we can use this. So real part of f d mu plus I times imaginary part of f d mu. So first we define the Lebesgue integral for unsigned measurable functions, and then we define it for real valued absolutely integrable functions, and then real complex valued absolutely integrable functions. So we require this condition of absolute integrability, because when we have absolutely integrable functions, then for example if it's real valued, then both these integrals, these are finite. So this is a finite integral and this is also a finite integral, and so the difference is also finite. So this is only when f is already absolutely integrable. Similarly, if f is absolutely integrable and complex valued, then both these integrals of the real and imaginary parts are finite. So for this definition or terminology, suppose that P is a property about points of x. So we say that P holds almost everywhere, or mu almost everywhere sometimes. If we want to emphasize the measure, then we say it's mu almost everywhere if the set of points, so let's take the set of points such that P does not hold at x, this is a measurable set, and the measure of this set is 0. So this set of points such that P does not hold at x, this measure is 0. We will often work with complete measure spaces, so we can also rewrite it as the outer measure of this is 0, then it will automatically hold that this is a measurable set if x is complete. So let me write it as a remark. So if x b mu is a complete measure space, recall that a complete measure space is one for which all subsets of null sets are also measurable. So if x b mu is a complete measure space and the outer measure of this set of points on which P does not hold equals 0, then this implies that this set belongs to the sigma algebra B. So we will often work when we have to assume that X B mu is a complete measure space. So for example, so let's take an example of a property which holds everywhere, so holds almost everywhere. So let F be an unsigned measurable function on X. So we say that, for example, that F equals 0 mu AE in short. So this is mu almost everywhere, if the measure of the set of points such that Fx is not equal to 0, this is 0. Now note that this is actually automatically a measurable set, because we can write this set of points for which Fx not equal to 0, this is equal to the union over natural numbers of the sets x in X such that Fx is greater than or equal to 1 over n. So when you take the union, you get this set of points for which Fx is not equal to 0, and of course these are measurable because F is a measurable function. So in this case we automatically have that your set of points for which this property does not hold, which is F equal to 0 does not hold, is already measurable, and we say that F equals to 0 almost everywhere if this set has measure 0. Similarly, if F and G are unsigned measurable functions, then we say that F equals to G almost everywhere or mu almost everywhere if the measure of the set of points such that Fx is not equal to Gx is equal to 0. So we see that we can take various properties of our functions or even the space X itself, and we have this notion of almost everywhere when the complement of that property has measure 0, or the negation of that property has measure 0. So we have actually a nice result about almost measurable functions. So let X be mu be a complete measure space, and so then let me write two properties actually. So first one is that if F and G are unsigned functions, are unsigned but not necessarily measurable, but we suppose that one of them is measurable, and either, so first let me write that F equals G mu almost everywhere, and either F or say G is measurable, then the other one is also measurable, then G or F is measurable. Similarly, we say that if Fn is a sequence of measurable functions, for which Fn converges to F for almost every x, which is mu almost everywhere. So this means that Fn might not converge to F at points whose measure is 0. So this means that the set of points such that Fnx does not converge to Fx has measure equal to 0. So if you have a sequence of measurable functions which converges almost everywhere to a function f, then f is measurable. So this is a very nice property of Lebesgue's measure theory, that we can leave out set of measures 0 and we can retain many of the important properties of measurability and absolute integrability as well. So this is Lebesgue's philosophy. So it says that in informal terms, it is sufficient to look for properties that hold almost everywhere for all practical purposes in Lebesgue's measure theory. So measurability and absolute integrability, we can also look at pointwise convergence almost everywhere and so on. So this gives us a lot of leverage and a lot of free space to work with measurable and absolutely integrable functions. So another property here is that if you replace, so let me write it down. So let me write the third property in this lemma, is that if f is an absolutely integrable complex valued function and g is another function complex valued such that f equals g mu almost everywhere, then g is also in L1. So we have defined an absolutely integrable function as one whose modulus has a finite Lebesgue integral as an unsigned measurable function, and if you take any other g which agrees with f for a large set, which means that the complement of that set has measure 0, then g also belongs to the set of absolutely integrable functions. So I am going to leave all these three as an exercise. So check all these three properties. So this is an exercise for you. So just by following the definition, one can show these properties quite easily. Now let us look at some important properties of absolutely integrable functions. So the first one is called Markov's inequality. Markov's inequality. It's also sometimes called Chebyshev's inequality. So this says that if f is an L1 function, then we have the following inequality, which is that the measure of the set of points such that, so this is for any finite number lambda finite positive number lambda between 0 and infinity. So the set of points for which fx is greater than or equal to lambda is bounded above by 1 over lambda with the norm L1 norm of f. So it's actually quite easy to show. So let me write the proof. So we know that, so we have that fx is greater than or equal to lambda times the indicator function of the set x belong to x, such that fx greater than or equal to lambda. So this is a an easy inequality to verify, because if fx is so this should be mod f, sorry. So we have this inequality with the mod. So if f is unsigned, then we can remove the mod, but in general we have a complex valued function, so we take the modulus of fx. So the modulus of fx is greater than or equal to lambda times the indicator function of this set where the modulus is greater than or equal to lambda. This is because if x does not belong to this set, then the indicator function will give you 0 and you will only get, so there is an x here, you will only get 0 on the right hand side. So you will get mod fx is greater than or equal to 0, which is always true. And if you have x belonging to this set, then you will have a 1 and you will get mod fx greater than or equal to lambda. So let me write, so if x does not, so let me write this set as s lambda. So if x does not belong to s lambda, this implies that modulus of fx is, so lambda times chi s lambda of x is equal to 0. So this implies that mod fx greater than or equal to lambda chi s lambda x holds, and if x belongs to s lambda, this implies that lambda chi s lambda x is equal to lambda simply. This implies that mod fx is greater than or equal to lambda holds because x belongs to s lambda. So in both cases we see that this inequality holds, and now we can use the monotonicity property. So note that this function on the right hand side, this is a simple function now, simple measurable function, and so we can integrate on both sides. So we get, so by integrating on both sides, we get lambda times the measure of this set s lambda is less than or equal to the integral x mod fx d mu, mod f d mu, and this is nothing but the L1 norm of f L1, and so the measure of this set s lambda is bounded above by 1 over lambda and times the L1 norm of f. And note that lambda is between 0 and infinity, so we can divide on both sides by lambda and we get this inequality. So this is Markov's inequality, and as corollaries, two important corollaries. So the first one says that if f is an absolutely integrable function and the norm, the L1 norm of f is 0, then f equals 0 mu almost everywhere, and vice versa, which says that if f equal to 0 mu almost everywhere, then also the L1 norm is 0. So this is an if and only if condition. So it says that if L1 norm is 0, if and only if f equal to 0. The second condition, the property says that if f is an L1 function which is an unsigned measurable function, then f is finite almost everywhere. So remember that for unsigned measurable functions we allowed the value plus infinity, and so this says that f is the set of points for which f takes the value plus infinity has measures 0. So let's prove this using Markov's inequality.